So let's now look at the relationship between the focal length and the radius of curvature. The focal length and the radius of curvature. In this case, we are looking at a concave mirror, and we've taken this ray in orange. It's a paraxial ray, so it meets the condition that it's close to the pole. Also, it makes a small angle with the normal. CM, C is the center of curvature of this mirror, and M is the point of incidence. So CM is the normal and the point of incidence, and the incident ray is making a small angle. Theta in this case is a small angle. That is the assumption we are making. So what is the relationship between the focal length, which we write as small f, and the radius of curvature, written as capital R? So note also that the distance FP, F is the same as the distance FP, and the radius of curvature is the same as the distance from the center to the pole, which is CP. Now let's look at some geometry here. First off, the incident ray makes an angle theta with the normal. So by the law of reflection, it is reflected symmetrically about the normal, and the reflected ray also makes the same angle theta with the normal. And also, since the incoming ray is horizontal, it's parallel to the principal axis. So if this angle right here is theta, what is this angle going to be? That angle is also going to be theta. So this angle here is also going to be theta. And then what is this angle right here? So if you look at triangle CFM, this right here is an exterior angle, and the exterior angle equals the sum of the two interior angles. This is something you might remember from your geometry. So this angle is equal to the sum of this guy and that guy, so that is 2 times theta. And now let's do some trigonometry. So let's look at triangle CMD, triangle CMD, and triangle FMD. We're going to look at some trigonometry in these two right angle triangles. This here is a right angle, so we're dropping a perpendicular from the point M onto the principal axis, so that there is a right angle. So these two triangles, let's write down what is tangent of this angle here, theta. That equals the opposite side over the adjacent side. MD is the opposite side opposite to theta. The side adjacent to theta is CD. And a triangle FMD, tangent of 2 theta is this angle here, is again opposite over adjacent, that is MD over FD. Remember, we said now that theta is small, which means, when theta is small, it's close to 0. Then tangent of theta is almost equal to theta. And if theta is a small angle, so is 2 theta. So tangent of 2 theta is almost equal to 2 theta in radians. So now if we substitute, if you write tan theta as theta, and tangent of 2 theta as 2 theta, MD over FD, and this thing here is equal to MD over CD. And I can substitute this value for theta, right here. When I do that, what do I get? Twice of MD by CD, twice of theta, which is MD by CD, equals MD by FD. And so MD cancels out. What do you get? You get FD equals CD divided by 2. And now when M is close to the pole P, then the distance between D and P is very small. So the distance FD is almost the same as FP. FD is almost the same as FP, which is the focal length. FD is the focal length. So we can write this equation here. FD is going to be the same as the focal length. And CD, what is CD? CD is almost the same as CP, which is the radius of curvature, and then divided by 2. So the focal length is equal to the radius of curvature divided by 2,